Since there is a new student in this class today, so I will introduce why we study linear algebra when you study mathematics, and why many mathematicians say linear algebra is very important in mathematics. By giving some examples. Actually, I have a point I want to introduce what is dual. However, we are using the textbook Elementary Linear Algebra of Anton. So in this book, there is no concept of dual. So I will, if I can introduce dual, then I will explain that. Linear algebra is simply a subject studying about linear equation, and I'm sure you know what is linear equation. And I will explain a little different way. Linear equation is you will think x1 plus x2. So there is coefficient and xn equal b like this form, and I wanted to explain my major. My major is algebraic geometry, and algebraic geometry is based on linear algebra. However, it is not have linearity, because this equation has only degree 1 variables, and so I will explain this time. It is a polynomial of degree 1, and if you construct some situation from the real world, then you will get more higher degree equations, and you might want to get the solution. Actually, linear algebra is very, if I explain like this, it is just polynomials of degree 1, then you might think there is a few examples in the world to explain real world. However, it is using many variables, so actually there are many situations to explain by using linear equation and linear system. So by solving these equations, you might get some optimization solution, or by using by using the property of matrix, you will get some geometrical useful too. So let me give one example. Actually, for the first example might not be a good example. However, I want to convey that the matrix is very useful too. So let's imagine the situation. There is 4 series A, B, C, D, and I'm certain you will know what is coupon, and I bring this question from coupon. Coupon want to deliver their items to the owner of the items. So in this sense, they might want to get the optimized way how we go to get the series, and we bring the items to the order of items by using at least cost. So there are 4 ways, and there's no way to there are some ways how to go. There is this graph, and in this graph you will start from A, and A is the company's position, and every item is started from A, and by moving another city, they will use their costs like money or some oil or other they will use workers. Then it is needed some fee, and I will input the fees to move another city to another city, like this. When you go to A from B, then it is takes two costs, and when you go to B from B to A, then it is costed just one cost. Like this, if oh wait, maybe I miswrite in my notes, so I like this, then okay. Yes, 7 and 7. Okay, I will rewrite it 8. Then from this, we might construct matrix, and actually there are many kinds of matrix to have this information. The kinds of matrix, there are many kinds of matrix. It is not needed it is not needed square. However, in this time, I will introduce basic matrix. If you see this graph, then you might want to explain this graph to matrix like the cost from if you go to from A and you want to go B, then it takes two costs. And if you go to from B to A and you want to arrive to A, then it will be cost 1. Like this, if you write all ways, then from A. There's no ways for own cities, and from C to B, it takes 7. D to B, D to B 5, and A to C 4, B to C is 3, D to C is 2, D to A is 4, 9, A to D is B to C. B to C. Oh, it is 6. Thank you. A to D. I'm not good at reading number. B to D is 8. Is it right? A to D is A, B to D is A, C to D is 5. Like this form, we might write this form. And if you just this graph, then you might not get the solution of the at least cost for at least cost. However, by constructing this matrix by using, we give the if we go to A from B, then it will record these entries. So by using proper operators, like we want to show A to B and B to C and C to D, D to A. Finally, we should return to original position A. So this graph will explain A, B, C, D, A. And we use this form from this matrix, then it will return like 4, 6, 2, 8, 8, 5, x 1, 3, 9. then you might not know what is trace. It is simply just summation of diagonal entries, the main diagonal entries. So if we call this operator is sigma, then by calculating trace sigma matrix, we might one solution. It is not final solution because we should compare another solution. What is minimum? So from this we can construct the solution will be like this form. I said it is proper because we do not learn what is proper operator in this system. However, if you want to get the number of sigma, then we will think about it is just change the orders of BCD because we will start from A and we should return to A. So the changing the three numbers is there are three factorials operators, proper operators. So I give it just 4 series. However, in Korea, Korea is I think not large countries, not larger than other countries. However, we have a lot of many cities. I guess over 100 cities if you consider small city too. Then it will take more 100 factorial and it will take too much time. And by analysis this matrix, or you express this graph to another matrix, then you might get the more good method to find the solution. And sometimes linear algebra gives this solution. However, it is I bring this question. However, we do not know what is the best solution, best algorithm in this problem because it is millennium problem. How many we reduce the solutions speed solutions. How many we reduce the solution is do not well known. So if you get the answer, then you might get years better, maybe. So at first time I say that it might not be a good example because I do not give the solution and I do not give how to solve this way. Actually, it is needed until now. It is needed n factorial times. We reduced this time to the n and to the 2. Not n to the 2. It is the best way we know. If you if you are interested in the solution, then you might find travel salesman problem. This problem is called the traveling salesman problem. So simply we say it. TSP problem, and it is a same problem to solve millennium problem. It is P versus NP problem. This example was my interesting, and next I will give simple example, of course. In company, if you manage your company, then you will get the optimized solution in some situation. Like if you consider you are made the items A and B in your company, and it is made from some material X and Y, and by using 3x and 2y, and B is made from 2x and 1y, and if you have alpha x and beta y, then you might construct from these two matrix alpha equal 3x plus 2y, because we have alpha's x is material to make items A or B, and beta 2x plus 1y. If you have 18x and 16y, then you will input 1860. By solving this equation, and we usually change its linear system by using matrix, and you can get the solution. It is not. Wait. You can get the solution. How many x and y is needed? So I give it just 2 items. Usually, many companies does not solve just 2 items, and they have a lot of items. They will have a lot of material. By calculating the matrix, by using computer, you can get the optimized solution, and also by analysis matrix, you might get the faster solution, and it will give some revenue in your company. Of course, today I prepared today's final concept is geometric of matrix, and it is also used in computer system, because if you play some computer game, then your characters will move to another way, and in this system sometimes you might consider how they can move, and they have some moving, and in this system they are using matrix, geometrical concept of matrix, like if they are positioned x and y, and it is just characters, your game character, and if you want to rotate left side, then it will be turned in the game world. Then it is in this system, if you construct just character, then by using matrix, you will rotate, or you will move for each part of characters. So by analysis the mathematics, you might get some useful tool to enjoy your real world. So it is my motivation why we need to study linear algebra, and it is very useful tool in real world. To elaborate a bit, this concept is purely my own philosophy, but I believe that mathematical relation of metric in algebra, it is similar to polynomial in my philosophy. And it is related to geometry because I explained my major is algebraic geometry. Oh. And geometry has some vector system because we should move. We will give the position in geometry. So usually we give vector space in geometry, or we just give topological space. And in this sense, the algebra's dual system will give, sometimes will give the concept of geometry, like, and also the geometry will give some algebraic concept. If you consider the graph, and you might denote this graph x-axis and y-axis by inputting the vector v, and this vector v, we might show what is v is 2, 3, like this form, and this means is vector v is made it two sides of two sides of x-axis and three sides of y-axis, and like this we will express the vector v like this form. And this means we denoted algebra to geometry because it actually x is a coordinate function to vector to real world. If we give v, then it will give 2. And y is also a kind of function. And if you give v, and if you the y gives you number 3. And this is a dual map of vector space. So I wanted to explain dual, what is dual. However, in our textbook, there is no concept of dual. So sometimes I might show some dual's property because it is related to geometrical concept from algebra, and from algebra, by using duality, we might get some algebraic concept. Actually, algebraic geometry are studying, this subject studying some geometrical concept by using algebraic tools. Conversely, to get some algebraic information by using, we get the information by using geometrical concept. Okay. Then I introduced the motivation why we learn linear algebra. So let's enter to our main lect. First, I explained a little about this in the last class. However, I will explain one more. In this section, we will study some metrics of various form. And the first form is diagonal matrix. And diagonal matrix is a scalar matrix in which all diagonal entries has some number, and another all entries are 0. Except the main diagonal. This matrix is called a diagonal matrix. For example, we might see some diagonal matrix, like just it has the main diagonals entries and another entry is all 0. Of course, then just 1 by 1 matrix is also diagonal matrix, and identity matrix is also a kind of diagonal matrix. And zero matrix is also diagonal matrix because there is no there is all it has all 0 entries for non the main diagonal and position. In diagonal matrix, it has fairly good property. The following property. Diagonal matrix is we want to get the information invertible, because if the matrix was invertible, then we will get the solution more easily by calculating. I think it's convertible. If we have a linear system like this form, by using inverse matrix, we might get the solution easily. So it is very important information of matrix. And diagonal matrix case, if and only the diagonal matrix is invertible if and only if all of its diagonal entries are non-zero. And I written the proof in my notes. If I explain a little bit, it is if it has 0 entries, then its form, if it's reduced the echelon form, will be 1 1 1 1 finally 0 1 1 1 1. It will have like this form by using elementary row operation. And in this form, we to have we might show to have invertible matrix. It has or 1 entries in reduced echelon form by using Gauss-Jordan elimination. So in this form, will not have all rows have 1, so it cannot be invertible. conversely, if it has all these diagonal matrix entries are all non-zero, then it will be all 1, so it will be invertible. And I think it is very good property, and diagonal matrix is very simple matrix to deal with ourselves. However, sometimes you might think it is very strong condition. So the previous mathematicians think about more weak condition of matrix. It is triangular matrix, and there is two kinds of triangular matrix. One is upper triangular, and another is lower triangular matrix. It is also performed in a square matrix. So the matrix is called it upper triangular. If it's all the entries below the main diagonal, the main diagonal and are all 0. That means if you construct a matrix, it has upper triangular side entries and another entries all 0. Similarly, we can define the lower triangular matrix by similarly. It's all entries above the main diagonal. All are all 0. I explained it. It is more generalized definition by diagonal matrix. Why I say this is, if the matrix was diagonal matrix, then it has 0 elements below the main diagonal, and also it has 0 and all 0 entries upper the main diagonal entries. So from this we can see the property of diagonal matrix is upper triangular and lower triangular. So there are some property of this. triangular, upper triangular and lower triangular. From the definition, it has the difference. The below side and above side, they have all zero entries. So the first property is barely makes sense. The transpose of lower matrix, lower triangular matrix is upper triangular. Conversely, if you transpose of upper triangular, then it will be lower triangular. And the second property is, if you calculate matrix multiplication in lower triangular, matrix multiplication, then you will calculate each entries by using row column rules. Then it's the above side is all zero, so by calculating this, you might get diagonal entries, and if you choose more upper side, then it will be all zero, and it has some entries in lower side. So these properties also make sense. Lower triangular matrix is closed under lower matrix multiplication. Also, if you choose upper triangular to upper triangular, then it will be give upper triangular as the result. If I read it, then it is also makes sense. Next, I give the property of diagonal matrix. If its main diagonal entries are not all zero, then it is invertible, and this property is induced to triangular matrix too. So a triangular matrix is invertible if and only if its diagonal entries are all non-zero. And it might be induced from the property B, because we calculate the main diagonal entries, then it will be multiply each diagonal point. So from use this property, then you might get the solution, the fact of this. And so from this sense, if you calculate the inverse, that means it has all non-zero entries in the main diagonal. Invertible or triangular matrix is lower triangular. Matrix. Conversely, upper triangular case also satisfies the statement. Okay. That's the second property. C. Yeah. Okay, it's okay. Diagonal. Row column. Determinant. Yeah. Yeah, right. It is also correct. The main determinant. Yeah, right. Yeah, it is true. It is related to determinant map, and why the reason why I didn't explain determinant is we have the concept of determinant in another chapter. So explain that. It is very important map in matrix for the information determinant because it gives the invertibility, and also it is continuous map. So in geometrical concept, it is really important map. So sometimes it is as a side brief note, determinant map. We will define its a matrix to the base field. We will use only real number, and these this map to the base field. We define this map the many kinds of these maps after you study mathematics a lot. And it is I don't know why I started this story. It is very important. So I will explain determinant more in more detail after. Yeah, that's correct. And next we see the diagonal matrix and triangular matrix, and next we will see the symmetric matrix. As a name, you might guess what is symmetric matrix. It is also a square matrix, and which satisfied the symmetricity. Then we will say it to be symmetric, and the symmetric property is the transpose is A equal to the transpose of its own matrix. That means its entries. GI. No, IG. That means AIJ entries is same AJI entries. If I give some examples. If you see this example, then I'm sure you can understand what is symmetric matrix. It is if you do transpose of the matrix, then each element, each entries are same for each side, each below side. Of course, 4x4 case also. I will make simply. Then for each entries are symmetric. It's transform. If we denote it A, then A transpose is same to A. We say this matrix is symmetric. And of course, the diagonal matrix has all zeros except the main diagonal, so it is also a kind of symmetric matrix. Because diagonal matrix, transpose of diagonal matrix is also the same diagonal matrix. Can I turn off the heater? Can I? Okay. And from this definition, we might think the follow property of symmetric matrix. I will give AB is symmetric matrix. Then the first property is the transpose is also symmetric because it is same the own matrix. And if you operate transpose double, then it will be original matrix, so it is symmetric. And if you calculate the summation of A plus B or A subtraction B, then they are also symmetric because each entry will be subtract or will be edit for each entry, so its symmetricity does not change invariant from the plus or minus. And also, if you multiply the scalar to matrix, then it is also symmetric. It is also fairly trivial because by calculating some scalar to the matrix, then it will have just same entries for each converse entries. I will introduce one more property. It is theorem. The product of two symmetric matrices, you might think it is preserved to addition and subtraction, so you might think it is preserved by products of matrix. However, it is needed another condition also. Is symmetry if and only if the matrix is commute. Maybe I proved this property, or I think I missed the notes. I will check if I check the next time after this class, I will share the proof. Let's continue the next theorem. We say that the invertibility is very important in matrix, so its properties also you might think easily. Invertible symmetric matrix, then there is the inverse matrix, and it is also symmetric. Because we might see the property of matrix in the previous class. It is satisfied the commute of the operation inverse and transposition. And since A is transpose symmetric, so the transpose is same to the original matrix. So the inverse matrix says transpose is same to own matrix. This implies A inverse is also symmetric. And also there are another property also. If the matrix A is an invertible matrix, then we might get the invertibility from the symmetry, and then A matrix multiplication A transpose is, or A transpose product A are also invertible. It is easy to calculate because if A is invertible, then you might get A transpose is also invertible because it is just calculating the transpose, so it does not change the entries. And by using this property, then if A has transpose, then the transpose matrix is also has invertibility. So, and invertible matrix, when I explain the invertibility, the two invertible matrix multiplication is also invertible because think it is easy to explain by using determinants, because the students say that the invertible matrix is the matrix is invertible if and only if the determinant is 0 and the matrix multiplication gives the scalar multiplication of determinant. Like if you have two matrix A, B, then determinant A, B is determinant A and B, determinant A, determinant B, and from this, if two determinants are not 0, then it is also not 0. I think it is a little cheat because we didn't learn determinants. However, maybe I do not have a lot of time now. I will continue to other source to next topic. It is final. It is not. As a remark, you might think any matrix A, it does not need a square matrix. It's rectangular matrix. Then you might calculate A matrix multiplication A transpose, then it will be square matrix, because if its size is n by n matrix, then m by n product n by m. The transpose is just change the entries to column to row and row to column. So if you matrix multiplication to matrix, then it will be m by m matrix. And also, if we see the matrix, also A matrix multiplication A transpose is symmetry, because if we calculate the transpose of this matrix, then it will be A transpose A transpose by the operator of transpose. It same to the original matrix, so it is symmetry. And it is also side brief. If you collect all these from matrix, that means in n by n matrix, if you collect all these forms, then it is all symmetric. It will be all symmetric matrix. That and I think you might doubt to this fact, so I will give an example of this. If you have this matrix A, then its transpose is 1, 3, 2, minus 2, 0, 4, minus 5. It is minus 5. Then you might calculate A and A transpose. Did I calculate? Oh, I didn't calculate. Okay, let's calculate it. Then it is multiplied. Oh. We will calculate this. then it will be 2 by 2 matrix by calculating 1 plus 4 plus 16, then 21, and 3 minus 3 subtract 12 subtract 20. I will to calculate. Yeah, right, minus 29. Thank you. And it is also same because it is also 3 minus. Oh, it is not 6, it is 0, sorry. Because we have 0. Minus 17. Minus 17. And its column product that its row product column is also same equation, so its result is also 17, and the binary is 3. 90 plus 25, then 34. Is it right? Okay. So it is a kind of symmetric matrix. Similarly, if you calculate converse way, A transpose matrix multiplication A, then you might get 3 by 3 symmetric matrix. Before today's classes part, I explained our today's goal is geometrical information in matrix. So the chapter 1.a is the transformation, linear transformation. In this section, we will view matrix in a little different way, which are called the linear transformation. Until now, we analyze the matrix to get some solution of linear system. However, linear transformation gives another way by reading the matrix as column, because the matrix has row entries and column entry, and row entries gives the linear equation for each linear equations. However, if you read as column, then it will give vector. And the first time I said the vector is similar to geometrical information. So by reading column, the matrix, we will get geometrical information. So before to start, I will give a notation. Or one. We called it the solution. We denoted the solution like two form. One is sequence of number, and another is as column vector input matrix. We are inputting the solution. We get the solution. we calculate the matrix, we get the solution, and the solution form was column vector. So the former one is called it comma delimited form, and the column form is called it column vector form. And we will focus on the second one. And by defining a special column vector form, we will give we will read the information of solution. It is like this form. E1 is 1 0 0 0 0 and E2 is 0 1 0 0, and if there is n variables, n unknowns, we said it unknowns, then 0 0 0 0 1 is E1. These are also an element of vector space Rn, because there is n entries. And another vectors in Rn is expressed by linear combination of these entries. So if I write it, all other vectors in Rn are uniquely expressed as a linear combination of them. In my opinion, to make this linear combination, we construct vector space. And this set is called the standard basis vector for Rn. You might have some doubt for this property, so I will give proof simply by showing any vectors to as a linear combination of them. If C a vector x, it has x1 dot 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 xn, then it will be written 1 0 0 0 1 x2 0 1 0, similarly summation xn 0 0 1. Then if you calculate this, then you will get this vector, and it is a kind of linear combination of EIs. So you can see the fact. And if you made there is another way by changing the coefficient, then you might get two things is the same. So from this, you will obtain the results uniqueness. Let's get back on track. We are where section is linear transformation, we will get back on linear transformation. To begin with, we might need to the concept of function. A function has a rule. It should go to just one value. So if f is a function from x to y, then if you get an element in x, then it will give just one value in y. So it has a rule. It is a very crucial rule that associated with each element of a set. We call this domain of the function. And it corresponds to one and only one element. In a set called it codomain. So we say this function and transformation is also a kind of function, and it is transformation is a kind of function on vector space. So I explained what is I explained a form of vector space and the function. I think vector space is a little more mathematical. We didn't define the mathematical vector space, so I explained it is just space of vectors. It has vectors. More precisely, we define the definition of transformation. I said transformation is also a kind of function, so transformation T is a function with domain Rn and a codomain and codomain Rm. Then we say that T is transformation from Rn to Rm. Is a transformation N to Rm. So it is just it is same to function. However, its domain and codomain is made from vector space, and actually, of course, does not need it to same to number of n and m. Yeah, it is not needed to same. However, if we might think if n is equal to m, then it might be a special case. So we will call the linear transformation as another name. Which is called operator. On Rn. It is depend on the domain or n equal m, so you might say Rn also. So I actually sometimes use the name of operator, and it is also it is okay to think it's just function on vector space. So from this definition, the linear transformation, transformation can be used in manifold or another subject also. Of course, it is just function on vector space, and I think you are studying manifold now in this semester, and you will study the vector bundle, and in the vector bundle sense, you might use transformation, and sometimes they use the name transformation. Transformation. Yeah, it will be. Yeah. You mean operator can be used another case on except vector space? Yeah, it is true in a mess. So usually, if we say the operator, then we consider vector space also. Of course, they do not denote some. It is vector space and its operator. We might not say like this because sometimes it is trivial for mathematician. When I did. Wait. What time is it now? What time is it now? 22. Okay. In matrix, if we use the transformation in matrix, like okay, I don't know. We might consider we are analyzing to matrix, so we might consider in matrix, and the linear transformation is also might be formed matrix. However, it is not always. For this definition, means it is map, so it can be written function TA. Sometimes we might written the transformation to by using matrix A. This means if we give x vector, then its solution can be written like this form. Then it is also will be m n. Then we will give a vector in in. So it is also kind of linear transformation, and sometimes and it's in this case also if m equal to n, then it is called it matrix operator. We say this matrix linear combination. Not linear combination. What? Matrix transformation. And in special case, and if n equal to m, then it is called the matrix operator. I prepared another one. Oh, I prepared the special one, special example. We might not be express all transformation like this form, because if you consider the map x1, x2, 2 for a transformation T, if it goes to like this form, then if you try to find the matrix, then of course it is coefficient matrix, so its entry is fixed. Its entries all scalar entries. However, if you find it, then it might written like this form. By multiplying x1, x2, then x1 square plus x2 square, x1, x2. However, it is not coefficient matrix, so if you try another form, then it always needed the the variables in as the entries, so it cannot be written matrix transformation. So matrix transformation is a little special case in just transformation. And then I will introduce some kinds of transformation. I will share my video. So one kind first kind of transformation is zero transformation, and from the name you might guess what is this. And I will read 0 mn, and it is m by n geometrics. Then we might consider a matrix transformation by calculating 0mn to the vector x, and it will be always 0 vector, and this matrix is called it the zero transformation. Formation from Rn to Rm. And similarly, we have another special matrix which is called the identity matrix, and this matrix is also can be written linear transformation. I will define one more. I will write it in here. If identity is the n times n identity matrix, square identity matrix, because identity matrix is square matrix. Then we might define the transformation like multiply the identity matrix to the vector x, then it will give own vector x because its matrix is diagonal entry is all 1 and another entry is all 0. So if you multiply vector x, then it will give same value, same vector. So it is then it is same to identity map, and sometimes it is called it identity operator in vector space case. It is square matrix, so identity is square matrix. It can be called it operator. There are some properties of transformation, matrix transformation. I will denote A is matrix and TA is a matrix transformation. Then the first property is the 0 vector will goes to 0 vector, and it is easy to check. If you matrix multiply the 0 vector, then its linear combination form is all 0, so the result is n0 vector to m0 vector for the transformation, matrix transformation. And the next property is the scalar multiplication. A scalar multiple of vector can be can be goes out goes out to left side or right side. This is because if you consider the matrix scalar multiple to vector, then it can be written a k u. Of course, it is same, and it can be moved another way, left way. Then it is same to this. And the third one is the distributivity of matrix transformation. It's as the summation, of course, subtraction is 2. It can be distributed for each transformation as a image. This is also similar to this. If we written the matrix multiplication form, then we learned it can be satisfied the distributive rule. So it is same to TAU plus TAV. And these two properties, they are quite important in transformation case. So if I will give why it is important by proving, by showing a theorem. This marker is not be erased easily. This marker that does not erased. That did not erase easily. The theorem is 1.5, and I will give the previous notation. I will write again. T is matrix transformation from Rn to Rm. And if and only if the following statement is satisfied, the following relationship holds for all vector u and v in Rn and for scalar f. The first is the condition of B. K u is equal to K TU, and the second property is TU plus v is t u plus tv. If the if the transformation T satisfies these two properties, then it will be matrix transformation. And I think it's one way is very trivial, because by the definition of matrix transformation, by the previous theorem, we get that if T is matrix transformation, that it will be satisfied the property B and C. So this way is obvious. Obvious. And so we will prove converse way. So that means if the transformation satisfies these two conditions, that means there is a matrix A such that Tx can be written matrix multiplication by A. So we will find this matrix A. I explained all vectors in vector space Rn can be written the linear combination of standard basis n en if this vector is x1 to xn. So by using this property, we will find the matrix A. So let's define the matrix A like T1 TE1. E1 is this element. Then if you input the E1, then it will give some column vector, and then it is, if you multiply x, then it is give TE1 x1. Similarly, we will define T of E2 to T of En. Then, if we calculate A multiply x, then it is x1 TE1 from this. Like this, it will be written M T E N, and we have these two properties of linear of transformation, so it will make this form, because it is just scalar multiplication of E1 to E1, and it is just summation of two vectors in real vector space. Addition of two vectors in real vector space. So it is same to this form, and we defined this is vector x. So if you define the matrix A like this, then it is the matrix we want. This equation satisfies this equation. So if the transformation satisfies two property, then it will be matrix transformation. Of course, identity. We saw the three property of matrix transformation. There was one more property. It was, yeah. The first one was zero goes, if you input zero vector, then it will goes to zero, and by inputting the scalar 0, then of course it will be zero vector. So actually the previous theorem is also saying these two property of transformation. And transformation satisfies the two property, then it is called it matrix transformation. And sometimes we say it linear transformation if the transformation satisfies these two property. So when today's class, I say the linear transformation sometimes, and the reason is if the transformation satisfies two property, then it is called it linear transformation, and we will deal with linear transformation often in linear algebra. Of course, this property is called it linearity. So from this property, we say this transformation is a linear transformation. The two conditions B and C of the previous theorem. We see the existence of matrix A for transformation. However, we might check the uniqueness to use this matrix A, because if we have another matrix B, then it can be written two form as linear transformation. So I will prove the uniqueness of linear transformation. The matrix of linear transformation. So let TA is linear transformation, and it's the same. TA and TB are matrix transformation, is the same linear transformation. If TA TB is same, then for X, then A equal B. I think it is same to this proof. This proof is similar to the previous theorem's proof because we inputting the standard basis E1 to E, and we might get this. But this matrix, these two matrices is same. However, it does not mean this form is unique, because if you change the another vectors, then the coefficient will be changed. Then by the vectors, like if it was the same x1 prime and another vector e1 prime plus x2 prime, e2 prime, I will define e1, I prime is, another one is 1 and ith entry is 0. Then by using this form, you might construct another linear combination, and this form will give another matrix. So if you choose same vector, then it will give unique matrix A. Every linear transformation, the vector, the linear combination. Maybe it is not uniquely. If I will give an example, if x is in R3 and its vector was 1 to 2, and it is written, it can be written 1 0 0, not 1, 1 scalar multiplication 1 0 0 plus 2 scalar multiplication 0 1 0 plus 2 scalar multiplication 0 0 1. It is just standard form, and we can denote this matrix as another form. If I use the last one, then it is hard. I will change the form. If I define 1 1 1 plus 1 0 1 1 plus 0 0 0 1, then it is also same to this vector. So by choosing another vector set, it will be called the basis. We might get another coefficient, and so but after we learn linear transformation, then it will give another vectors, because it is 1 2 2 is give this vector. However, this coefficient will give 1 1 0. Then we might guess from by calculating an operator to this vector, then it might be this vector by using linear transformation. We will learn about this soon. So its uniqueness does not mean the expression of the linear transformation is unique. It does not mean this sense. It is if we choose standard basis, then it will be unique. So let me give one example. Let's the linear transformation is give the vector x1 minus 3x2 minus 1 plus x2 this vector, then that means T is a linear transformation to R2 to it means T is transformation R2 to R2 3 R2 is 3, and we will verify T it was exercise, so wait. 2 1 1 minus 3 minus 1 1 1.4. That means it is 2 4 6 1 minus 12 minus 1 plus 3. And if you input this vector to transformation T, then it will give two dot 1 plus 4, 1 minus 3 dot 4, and minus 1 plus 4, then it is 6 minus 11, 3. It is same. I calculate. By multiplying the matrix, we can denote the transformation, the linear transformation T. I made some exercise, another exercise in my notes, so I hope to check the another vectors also, and then you might, or maybe the next exercise is finding this matrix A in as a transformation R2 to R2 and it is a good practice to understand the linear transformation, because it is fairly difficult concept for linear combination. So I want to find the matrix A. If you believe it is linear transformation, then it will be written by multiplying matrix A. So I want to practice. If you think that you need to practice for linear transformation, then I recommend to try to find this matrix A and B. And of course, I prepared some geometrical concept of linear transformation. However, let's be done in this class after the new student is invited. When the new student come the next class, I will explain the geometrical concept. Thank you for listening my class.